of the last homework on Wednesday, and on Wednesday I will publish on Blackboard the take-home exam that you will have to solve independently. Then do not get too much exposure to radiation from colleagues, and do not forget to bring it at the exam, which will be on April 10th as scheduled. It seems it was a kind of glitch with the communication between here Delft Eindhoven and Twente. I hope they can hear us, or me at least. We cannot see them. If there are any issues, you know, email is always working.
We can hear you.
Okay, it's great. I can hear you too, which is brilliant, you know. But we have to make a kind of choice, even sound or image, right? They don't work together. Okay.
Eindhoven, there's no students.
Then, if there is no student, maybe somebody will come later on.
Yeah, maybe.
Maybe.
The system is on.
Okay, thank you very much. Okay, then let us return to the floating point story. As we discussed last time, floating point has a lot of complications, and part of those complications are also conversions and exceptions. Then, while in integer representations things are clear, you may or you may not represent a number. If you don't have enough dynamic range, you cannot represent it, and point blank. In floating point, there are some issues like, you know, you have problems of conversion from different formats. Then from single precision to double precision, from different radixes. If you do, let's say, decimal floating point, you can represent numbers which are good for finance in a very good way. If you do radix 2 floating point, then some of the things may not work well. Then also when you do calculation, things may go beyond the representation domain, and then you have to do rounding. And there are some standard rounding modes, morning, and there are 5 of them. And most of the time when you execute a program, you have no clue about what kind of rounding you are using, right? If you probably, I assume you made use of floats in C programs, but you didn't say what type of rounding you are using. This is something which you can select. It is predefined, like rounding to nearest, time to even, but depending on what kind of calculation you do, you may choose one or another type of rounding. Rounding will influence your results. Then if you are computing an upper bound, you may want to do rounding in a certain way. If you are computing a lower bound, you may want to do it in a different way, because this will kind of introduce a systematic error in your calculations. Now, you also have exceptions, and exceptions are, you know, when you divide by 0, when you do a square root of a negative number, when you have an overflow or an underflow, or you have an inexact result. Then due to the calculation, you have something which cannot be exactly represented, and then you have to signal that. There are a couple of bits in the state register, which now are more. In integer ALU, you just have 0 and sign, and that's it. In here, you have more bits. Now, you also have to follow a certain kind of convention when you deal with strange operations, like when you add strange numbers. If you do plus infinity with minus infinity, what is the result? Okay, the result is not a number. And this is standard. I mean, all the floating point units which are obeying the IEEE standard will provide you that kind of not a number result. Now, when your program is executed and there is an exception, the exception is handled in a different way, which you as a programmer can control or leave it to up to the system. Now, usually we do not interfere, but when we want to drive the errors in a certain way and we want to control them, we can interfere and take actions when we get such strange results. Now, there are many ways to do rounding, and you can actually drop things, and this is called chopping. Essentially, if this is the unit in last position, I drop everything from here, and if all of them were 1, I almost lost a unit in last position. If all of them were, the majority of them were 0, I lost less than that. This is simple and will not create me any kind of headaches. Now, if I want to do some rounding, I have to compute something based on those bits. And that something will result in maybe an addition of a unit in last position here, which is actually a full addition. Then rounding creates an extra step, which is a full carry propagation. Now, there are many ways of doing that. I will not go into details on how you do this kind of rounding and how you do truncation, chopping, whatever. Now, you see that if you do a certain rounding or a certain chopping, you induce a kind of error. And in general, it is good to know what your error is. And here you have an example when you drop, those 2 bits after the decimal point, and you see, depending on how they are, you induce an error. And you have a mean error, which will hold true whether or not in the case that the input values are equiprobable. In some applications, however, the data profile is biased. Then the numbers that you are processing are not uniformly distributed, and then this error may change. Now, I just mentioned that rounding actually creates a problem because creates an extra addition. This is a method which can help you to do rounding without addition. And this is based on a lookup table. And practically, you take some of the bits and use them as an address. You look into a table, into a ROM, and you get the new value of those, the significant part of the number. This for sure is good because you do not get the delay of an extra addition. But in some cases, this may not give you a good result. Assuming that you had a unit in last position here due to the rounding, and then this will propagate, there are changes which may also go beyond the boundary of this bit. But the advantage of that is that you can do it fast. Now, the rounding, as I mentioned, you can do it in different ways depending on what you compute. Most of the time we don't deal with that, but assuming that in the future you'll have to do that kind of calculation of bounds, or you want to have a certain indication on the accuracy of your calculation, it's good to know that those things can be changed. Okay. then this is a extreme case of floating point. Then I take all my budget of bits, except the sign bit, and I invest that in the exponent. Then in floating point, we said, in order to trade, to do good business between fractional and integer, between precision and dynamic range, we gave budget to the fractional and to the exponent, and we did a good job. Now, if I deal with very, very large numbers, and I don't care that much about precision, but I want to have a big dynamic range, like I'm doing, I don't know, astronomy kind of calculation, I may end up in using such a system where all my all my budget is utilized for the exponent. And as you see, the exponent, it's actually a logarithm and can be fractional. And I have here an implied radix point, and I can play with it. It's not part of the representation, but I can have it in my mind, and I know where it is. Now, that kind of representation is not usual in computers, but we may use it whenever we need to do kind of astronomical stuff. Now, this is very nice when you have to do multiplication and division, because the multiplication of two numbers, it's actually, if you brought it into the logarithmic space, then you will just add the two representations. And if you do division, you subtract them. Now, if you have to do addition and subtraction, then things are getting complicated. Okay, now, this is a kind of slide which is telling you the fact that if I'm using those bits for logarithmic representation, I get a very large dynamic range. I have some good precision close to 0, and then, you know, the accuracy is decreasing. Now, let us take a look on the floating point operations, how they are actually done, what is the required hardware, what are the complications, and to look a bit on the required functional units. Then addition, we start with addition, and as I said also last time, addition is by far the most complicated one and also the most problematic one. Then first of all, you have to do an alignment. Now, because otherwise, if you don't align the operands, you will not be able to add the significance. Then you have to bring them in the same domain. Now, in hardware, you can shift both of them, but most of the time you only have one shifter. And then you will have to route your operand to that shifter. After you do the shift, you do the addition. Some of the bits due to the shift will go beyond the representation. Then in the worst case, you may have to shift 31 positions, 32 positions, right? Then if they are very, very disaligned, they are out. Now, it makes sense to have some overlap, because if they are out, nothing is happening, there is no interaction. Now, when the overlap is happening, you know, you do the calculation, and now you have to normalize back. We rely on the fact that we always normalize. Now, depending on what I'm doing and the type of the sign of the operands, I may have to normalize in a different way. If I'm adding two numbers, they can be between 1 and 2. That's the standard number in floating point, but not 2, opening If I add them, I get something which is between 2 and 4. Then I will require a right shift to do normalization. If they are of different signs, when I'm doing the calculation, there might be a lot of cancellation, and then I may require a lot of left shifts. Then what I'm doing after I finish depends on what kind of operands I got and on the operation that I'm doing, addition or subtraction. Now when I'm doing those post calculations, I may get overflow and underflow, because all the shifts will have to be reflected in an update on the exponent. And if I am on the border and I'm trying to increase the exponent beyond the limit or to diminish it, then I'll have an overflow or an underflow. Now, this is the way a floating point adder is looking. When we are discussing about addition, we are just discussing about how to do this. Now, what is around here, it's overhead. What's around there, it's helping me to carry on an addition in the context of floating point. And as you see, there are two channels. There is a channel which processes the exponent. There is a channel which processes the significant. And there is also a bit of a braining here, because I need a controller which will decide, depending on the results, what to do. Then my floating point adder is not any longer a combinatorial circuit, the one that we are making very happily with ripple carry or whatever. It's a very complex structure, and with a latency which is not always the same. Then I have variable latency. Sometimes I can complete it faster, sometimes slower. And the addition in here, it's the one which I know for sure that will happen. But about the rest, sometimes things may or may not happen. Now, at the beginning, what I have to do is I have to unpack the values, the operands from registers, where they are stored in floating point format, and I have to bring them to the inputs of my unit in the right format. Then I have to take the significant and I have to pad it with the 1. I also have to look at the sign, right? In here I have the sign which is separate. But if I'm bringing it into my addition, I have to do 2's complement kind of representation. Then I will have now 2 bits which are in the integer part, and the rest will be after the decimal point. In the top of that, I will also have to check other things on the operand if there are some problems. Then the first step will be to see how much do I have to align. Then I have to compare the exponents, which will be a subtraction. Then I'm making a subtraction, and that subtraction will tell me how to align the significance. I mean, this result here will bring me an information, and based on that information, I will shift one of them in order to align. Now, as I usually have 1 shifter and 2 operands, I will have to route the right operand into the shifter, because I'm doing A plus B. Depending on the value of A and B of the exponents, I may have to shift A or I may have to shift B. Then I have to be able to route them in the proper way. Now, I also have to do a complementation, assuming that I'm doing a subtraction. Then the first part was to create the operands with the right sign and to pad them with the 0, which was to the 1 which is hidden. Now I have to do complementation. And again, I have to swap the operands if things are not possible on both channels. Now with that done, I am now ready to do the addition. And I'm doing the addition, and in the addition I get a carry in from the controller, and that carry will reflect the fact that I have done a complementation or not, and I will produce the carry out to the controller, and then essentially now the controller will check my result and we'll see how things are going. Then let us forget a bit the exponent for now and concentrate further. Now my result is not normalized. I may have to shift depending on the nature of the operation. I may have to shift right or left many times. This is done here in the normalization. Now after the normalization, I may have to round, because when I'm normalizing, now I put things in a certain position, and some bits may be out of the accuracy domain, and I should look at those bits and see if it makes sense to add a unit in last position or not. This depends on the way I am doing the calculation, what kind of rounding I have chosen. Now, this is implemented in here, okay? Then this guy knows about the nature of the result, but also knows about the status of my functional unit. What do I want from it? Now, I do rounding, and maybe I have to complement again, and then I do again a normalization, because due to the rounding, there is a non-zero possibility that I have to normalize again. And then now I normalized, and I have my result. In the same time, I also have to do things on the exponent. Then I'm doing a subtraction, and that one was in order to drive my shifter, but I have to work on the exponent too. Then I will choose the one, which is the dominant one, the biggest one. That will go further, and it will not be my exponent. It will be the start of my exponent. Now, depending on what I did here in normalization at this level, the controller will give me an amount of correction of the exponent. Then only after I finish that, I have the numbers which are okay for this adder to have the exponent. Then somehow I start with the exponent and I end with the exponent. Luckily, this is not a very wide adder, and I'm not done. I have now all of them, and I have to store the result in registers. To store the result in registers, I have to take out the 1, I have to put the sign in place, and I have to return to my initial storage. It took me a lot of time to explain you that. It also takes a lot of time in hardware. And as you see, when I'm doing this, I'm doing an addition. And then depending on whether or not I have to do rounding, this may take longer or shorter. Okay.
One question.
Yes.
What was the direct line from unpack to pack? On the right side, the direct line from unpack to pack.
Ah, this one you mean?
Yeah.
This means that actually there is the same format. Then you start with the format which is in the registers, and you have to end up with the format which is again in the registers. Then those are related. This is the reverse operation of the packing. Then I'm unpacking and then unpacking. That's the... Okay, now, how do I do the shift? I can use a max. And with a multiplexer, I can route each bit to my output. Then in here, I have 32 bits. Then this is my significant. And then I can route it with shift, depending on the amount that I have to shift. I can leave it as it is, one position to whatever positions. Now I have those in parallel, and with the amount that I computed by the subtraction of the two exponents, I know how much I have to shift. And these are the 5 bits there. Now this is a good design in principle from the theoretical point of view. However, that will create some problems, because you will have a very large fan out on your bits in the registers, because they should drive a lot of those muxes. Now the design in normal units is done in this way. This is not the same as that one, because that one is for 32 bits, this is for 16 bits only. And the idea is that you broadcast the bits of the amount to that kind of cells, which are muxes, and then in this mux you select things which are coming from your current position or from a previous position. And at each level you have a shift, which is a power of 2. Then if I have here a bit 1, I can shift 1 position. On this one I shift 2 positions. On this one I shift 4 positions. On this one I shift 8 positions. Now depending on the code that I'm getting, I can obtain all the possible shifts. And this is working in parallel on all the bits. Then what I have are my bits which are coming from the top. Then I have this structure which sounds a bit familiar or not. Yeah, it is kind of like the prefix structure, but in here I don't have carry operators, I have small muxes. And this is a better design. Now what you see is that this is not a bidirectional design. This is only shifting in one direction. If I have to shift into the other direction, I have to have another shifter. Okay. Now, this is a technique which you can help in order to speed up the calculation. In normal operation, when you don't take any kind of precaution, what is happening is that you do the calculation, and when you obtain the result, you count the leading zeros or ones. This is the sign, right? And if the number is positive, you have some zeros. If the number is negative, you have some ones. You have to count them. And depending on the amount that you are counting, you will have to do shifts for normalization. Now, you can do that after you finish the calculation, or you can do something which is very much similar with look-ahead addition. Then you work in parallel. Then from one point of view, you work on completing the addition. And in parallel with that, you have a circuit which is using P's and G's in the way we were using for addition in order to predict the number of leadings 1 and zeros. Which means that now, when I'm ready with this, I can directly do the shift, because I know how much I need to shift. And this can help me on this. Essentially in here, the normalization will start earlier than when I'm waiting for the result. I still have to have it, but I know in the same time how much do I need to shift. Okay. Then if I want to make a unit we saw that we have adders which are dealing with the exponent. We saw in the previous scheme two adders. We don't have to have two, we can have only one. Just make this two. Then the subtraction in the top and the addition in here can be performed by the same adder. And this can be used to do the rounding. However, in most of the cases, this unit is pipelined. And because it is pipelined, then I'm not sharing resources, but I'm doing, you know, I'm having specialized resources for each of the operation. If I don't do that, it makes sense to share them. Now, my significant adder has, you know, all the bits which I stored in the floating point number, plus the hidden one, plus the sign, which is not stored in the significant, but is stored in the floating point, and I have to take it. Now, in the top of that, my adder will also provide a carry out, which will tell me something actually about the overflow. And because those are 2's complement numbers, and I may get an overflow. And I also have to be able to keep my calculation under control. Now, what does it mean under control? It means that my results should be correct as I would have done the calculation with infinite precision, and then I do the rounding. Because infinite precision, I cannot store. My storage is limited, and I have to do a rounding, but I should get the same kind of result. Now, in order to do that, I pad my adder result with 3 bits: guard, round, and sticky. And they help me to get that kind of result. You should not assume that they will give me the infinite precision, but they will give me the right result as I would have done the calculation with infinite precision. And, you know, they keep bits which I'm shifting out in order to align the exponent, the significance. And if I'm making only one shift, you know, I'm getting into guard. If I'm making 2 shifts, I have guard and round bit, and then I have also sticky. And depending on how much I shift, they can tell me a different story. Okay. Now, this is an optimization which is trying to balance the delay of the addition regardless of what I'm doing. Now, I have now a duplication of my hardware, and it's based on the fact that if I do addition of numbers, and if they are of the same sign, the result is normalized or will require 1 shift to the right. The pre-processing may require more shifts. If I'm doing the other way around, if I'm doing a subtraction, then I may have here a larger post shift. And remember what I said, the design of the shifter, it's unidirectional. Then you have the, let's say this is not very important from, I don't know exactly why Parhami put that slide in here because it's a detail, but it's just an optimization which is taking advantage of the behavior of the operands depending on what calculation you do. And you have a controller which will look at your operands and will say you go on that or you go on that. And if you have more additions, you may try also to keep them busy, right? But I have to have enough floating point instructions, and I have to inspect a large number of floating point instructions. There is a always a non-zero probability that two of those will be one after the other. But this is just, you know, an optimization. Okay. Now, with the help of those 3 bits, when I finish the addition, I will do the rounding. Then, based on the number of shifts that I'm doing, I can get some of the guard around and the sticky back. And when I'm done, I will do an addition if required, and that will complete the calculation. Okay. Now, there are exceptions, and I like this one. Determining when inexact exception. This is what Parhami likes a lot, to leave you home exercise. I'm pretty sure you appreciate that, right? No? Why not? It's challenging. Then, when I'm doing the calculations, I have exceptions. And those exceptions have to be handled, and I may have problems with the exponents. And this is not part of this drawing, but there is an interaction between this control logic and a register, which is the status register. And I also have to do this zero detection. I can use the leading zero detection for that if I have it. Then I can remember for the shift, I was counting the number of leading zeros or ones. I can use that in order to do things. Now, if we are looking at multiplication, things are a lot simpler. Actually, you see here, multiplier divider. The structure is the same, except whatever you have here is different. Then, conceptually speaking, I have the same beginning and end. I have to unpack and I have to pack, because in registers, the format is different than what I process. Now, things are simpler because I do not have to bring the sign into the multiplication. I can do unsigned multiplication here. There is no point. I mean, why would I complicate my life? The only thing that I have to do here is to see that I have a 1, a hidden one, but the sign is going from top to bottom in just a gate. For the exponents, I just add them. For the multiplication, I use whatever I have best. And then, when I do the calculation, I may have to normalize, which now will require an adjustment of the exponent, maybe round, normalize again, and back. Then things in here are simpler, predictable, and the complication is coming from my capability of doing the multiplication, while previously the complication was coming from the requirement to align the operands and things like that. When you do division, it's the same structure, but now you don't divide, you don't multiply, you divide, and instead of adding the exponents, you subtract the exponents. In most of the cases, when you do floating point, you may need that kind of multiply add unit. You know it in digital signal processors that you have a multiply and accumulate unit. We discussed about that before. I think I mentioned before. You can have that also for floating point. Now, in the floating point, there is a complication, and the complication is coming You know, when we are dealing with that in integers, it was simple. That was your, here you say, header 3, and additive input was coming here.